Good evening, everyone. My name is Jules Damji. I'm the Spark Community Evangelist and Developer Advocate for Databricks. Wanted to welcome all of you to the Bay Area Apache Spark Meetup. It's great to see. I'm really happy to see all these people here. Remember, Apache Spark is not a cure to insomnia. It is euphoria for developers. So I'm glad to see that you guys are here. You're going to be hearing about Apache Spark for the next couple of hours. Wanted to really thank our host, Intel, in particular for giving us this particular auditorium and having us the opportunity to actually come from San Francisco and be here in the South Bay. We try to have these meetups on a regular basis once a month. If you're interested to sponsor, if you're interested to host us, and if you want to speak at one of these Apache Spark meetups, do contact me. We're more than willing to talk about it. Today we actually have two great speakers talk about how AI is actually changing the world, and also how structured streaming in Apache Spark is also introducing a new paradigm of writing continuous application. And I want to thank Intel. Give them a big hand, guys. Give them a big hand. And in particular, the few people in Intel who actually helped me a lot in organizing Julia. Can you actually stand up? You're a big hand. She actually was quite instrumental in getting this thing set up, so I really appreciate Intel. And today we actually have a notable introduction from Intel, Mia Zhao, who is actually heading the big data and AI efforts, and she's going to come and say a few things about what they're doing with respect to AI and BigDL, and she's going to introduce other two speakers from Intel. So Zia, please be on stage. Thank you.
Thanks, Joe. Okay, good evening. So before I get started, let me just do a quick check. So how many of you have worked with Spark? Wow, everybody. So how many have played with BigDL? Some. Okay, then you are here for the right topic. So I'm going to keep my discussion short and sweet. I know you are here to know more about BigDL and Spark, rather than hearing an engineering VP mumble about some irrelevant items. I do feel compelled to spend a few minutes sharing with you the history of BigDL and what Intel is doing in this area. You know, Intel has been working with the big data industry for many years now. Our vision is to enable the easiest and most complete big data analytics experience on Intel platform for our customers and partners. So at the beginning of this journey, we worked with our customers and introduced Hadoop into their environment. You all know Hadoop is a very cost-effective data lake solution for hosting and managing large volume of data. And then over the years, we also introduced Spark into our customers' environment so that they can derive business insights from the large volume of data, and so that they can leverage Spark's powerful data processing pipeline and develop analytics applications on top of that. And then in the recent couple of years, more and more of our customers are adding machine learning and deep learning workloads into their big data environment. And their asks, especially for deep learning, fall into a few buckets. The first big ask is ease of use. They want to leverage their existing data analytics pipeline that they have developed over the years. So they're looking for some deep learning capability to be able to easily integrate with the existing data processing pipeline. And their ask is quite, something like this. Please don't tell me that I have to stand up a separate cluster just to train my model. And then later I have to bring the model back to my existing data analytics application and integrate it into that environment. I want a consistent and integrated experience when using the deep learning module. Now the second ask from our customer was deep learning at scale. So because they have large volume of data distributedly stored, and they want to apply large volume of data for their deep learning for much improved training accuracy, and thus deep learning at scale. Now other asks from our customers include lower cost of ownership and shorter training cycles. So when we worked with the first one or two customers, our reaction was that should be pretty easy, right? We should just port some of the existing deep learning frameworks onto Spark, and problem solved. We bring the benefits of the two together. But when we started testing it in the lab with our customer, it turned out that solution is not that great, because the existing deep learning frameworks, like a Caffe or some others, are not designed to work with big data platform like Spark. The integration is not coherent. Actually, you wouldn't be able to have the data level or model level integration at all. So that's one. We said, we have to do something different. We have to develop deep learning framework organically on top of Apache Spark. And so that it will naturally inherit the scalability from Spark. It will naturally inherit the data parallelism from Spark. And also this framework needs to have feature parity with existing deep learning frameworks like Caffe, thus BigDL. So Jason Dai, I think, right, he's shown here in the picture. He's our chief architect, and he worked very closely with the team and put a lot of effort to design and develop BigDL. Actually, our program manager, Radhika, is also here today. So basically, we worked really hard for this project, and we open sourced the BigDL 2 months ago. And the very first partner that saw the value of BigDL was Databricks. So Databricks reached out immediately after we open sourced the BigDL, and they said, we're going to integrate it into Databricks platform and making an end-to-end deep learning pipeline available for our customers. And then following Databricks, a few top-tier cloud service providers, top-tier telco customers, manufacturing customers, and financial services companies reached out to our team wanting to deploy Spark and BigDL into their environment. And also news media coverage is just wonderful. And even this week, I saw a news article from InfoWorld where it says the most popular deep learning frameworks include TensorFlow, BigDL, and a few others. So considering we only open sourced the BigDL 2 months ago, this is a significant progress that we're seeing. So we're very thrilled with what BigDL can do to our customers and partners. And we look forward to working with you all to bring more value to the big data industry. So with that, thank you very much and enjoy the rest of the event. So Joe told me that I need to introduce the next presenting team. So it's with great honor that I'm introducing two very talented technical people that we have on the team, Jenny and Sergey.
Hello, everybody, and welcome. I was just joking with Jenny that Zia is doing so good. We can just go grab ourselves some pizza because she already covered half of what we were going to talk about. Jason Dai, yes, our senior principal engineer and chief architect. Despite his picture being here, he's a very modest guy. Last night he begged me to remove his picture, but he was overwritten. So what is BigDL? As Zia said, BigDL is another library. It exists on the same level as MLlib or GraphX or any other parts of Spark infrastructure that you're familiar with. It's a standalone library. You easily download it and build it, and it's there for you. Why BigDL? This slide you're probably familiar with. It's a shameless steal from Google NIP's paper. The point here is that deep learning and machine learning systems are very complex. They have the whole pipeline, and it's best implemented in the distributed fashion on something like Spark. And therefore, Spark-based deep learning library is a natural fit for implementing deep learning algorithms. What's good about BigDL? It's natively integrated with big data Hadoop ecosystem. You do not need to change anything in your cluster infrastructure. It is distributed. It can scale 2, 5, 10, 100, and more compute nodes. It's built from the ground up to be this way. It doesn't need to be adapted. It sends compute to data. It's fault-tolerant because it's on Spark. It scales incrementally. You can deploy it on as many clusters as you want. You can run it on one cluster. I don't know why you would want to do it, but you can do it. And it shares resources dynamically. Benefits obvious, right? You write your BigDL applications just as standard Spark programs. And it runs on top of existing clusters. Of course, it adds familiar deep learning functionalities to Apache Spark. It's high performance. Why? Two things. One, it takes advantage of Intel math kernel library, meaning whatever compute task is being implemented, it's been implemented most efficiently because we, Intel, know how to best do it. And second, because we built it from the ground up, we were not tethered to any other framework. We were able to make some algorithmic improvements to the deep learning frameworks. And it scales out. It uses all reduce frameworks and so on. By the way, my personal experience with it, as we were installing Spark on other frameworks like Amazon and Microsoft Azure and so on, believe it or not, it took me longer to figure out what should be proxy settings on my party to go outside Intel than it took me to actually install the thing on a different cluster. It allows us to analyze the big data. It adds the deep learning functionality to what you already have in your workflow. It is a direct plug-in into existing ELT data warehouse functionalities, into your feature engineering pipeline, and whatever else you might already have. So on to features. So this is how BigDL works. If you look at this closer, you'll realize it works no differently than any other Spark component. You have your Spark program. You pick up, you instantiate your Spark context. You have a BigDL library with MKL support inside. In a distributed fashion, you span multiple workers using standard Spark jobs. And the workers communicate with each other using block manager. And you have the entire chain of your big data processing. We're not asking you to learn anything new. We're not asking you to do anything new. Whatever programming paradigms you use in Spark, you continue using them. Now, this is a really cool thing. We're not asking, if you happen to have ResNet model or Caffe model or Torch model, we're not asking you to throw them away. If you have a model that you like, that you trust, that your customers trust, that you maybe deployed already in production on a single node system and you're happy with it, you can take this model and drop it into BigDL. You can take your ImageNet, ResNet, drop it in a folder in the infrastructure, point BigDL to it. It'll happily pick it up and run image inference with it. If tomorrow you don't like everything about this model and you want to fine-tune it, you can fine-tune it on other framework, or you can fine-tune and retrain the model within BigDL. And later you can take it out and take it back to where it came from and continue working. Why is it a cool thing? Well, first of all, it lets you get started easier. Second of all, our experience has been that in big companies, data scientists live in this silo. Data engineers sometimes live in this silo. It's rarely the same person. So your data scientist can train and tweak and adjust their models here, and then you just take them and drop them inside your big cluster, and the model runs in a distributed fashion within the BigDL. It integrates with Spark ML using transformers. We support Spark 1.5, 1.6, 1.6, 2.0, and I think I even had it running with 2.1. We open sourced BigDL back in 2016, but we continue developing it. Just recently, we added Python API support. I don't know if you can see it on the right, but it's your regular Python. You can use your NumPy, Pandas, whatnot. You take full advantage of Jupyter notebooks, same way as you would if you were writing in Python scikit-learn. And we even hooked up TensorBoard for visualizing your learning experience and helping you to tune your parameters, because now you can visually see how your loss function is behaving and so on. I'm going to switch over to the demo right now. Hope it works. And this is, yeah. What is it? It's Lynette. It's very simple. Everybody knows it, right? You import your libraries. First comes Panda, then Daytime, and then that layer, that's your BigDL. And then you have optimizer support, and that's it. And then we start coding. What do? First, we pull the NIST database. In case somebody doesn't know what Lynette is or what NIST database is, very old, I think late 80s, early 90s, written character recognition. MNIST database has tons of written characters. Lynette 5 is a convolutional network that allows for character recognition. So what do we do here? We pull this data from a NIST database, store it somewhere. Of course, we normalize the sample. We do data engineering, pre-processing, the usual thing, right? Then we create the model. What do we do here? Spatial convolution, pooling, then your sigmoid-like hyperbolic tangent function, then another layer of convolution network, pooling, then we reshape it. We're done. Very similar implementation to what you would find anywhere else. Even if you were writing it in scikit-learn, you would probably write something very similar. Of course, it's all done within Spark context, as you would expect. Configure optimizer. Right here, we're using stochastic gradient descent. Could have used the AdaGrad. Could have used something else. It's just a matter of choice. We train the network. We inspect prediction results. And then we inspect the model. When this whole thing finishes running, we'll get some curves. And it runs fast on this machine. I'm going to kick it off in a second. It's going to run probably in about 2 minutes. On my old laptop and virtual machine, it runs probably about 10 minutes. But doesn't really matter. Trust me, it works. It runs very fast. And with this, I'm going to kick it off and give it over to Jenny, who is going to continue.
Yeah, I'll continue the introduction. Sergey just talked about the support of the TensorBoard. So later I'll show you the visualizations of the TensorBoard with BigDL. Okay, so BigDL also have a feature to integrate with other Spark components like the Spark streaming. We can integrate with the Spark streaming to do the runtime training and prediction with the different data source like the Kafka or HDFS. And also, we can integrate with the Spark SQL, data frame, and even the most latest structure streaming. And here's the example for the integration of the data frame, we create a BigDL UDF, which is a user-defined function on the Spark SQL. And this function is to do the classifications for the images. And we integrate this UDF to the applications. So the UDF can process the columns from the data frame. The data frame can be even the batch-based or the stream-based. And it gets data from the Kafka or the file system. And then after the UDF, after we query with the UDF, we can get the filtered data frame. So you can see in the right diagram is an example of this. We use the UDF named image classifier, and we use this UDF to create a new column, which is image type. And with this image type column, we can filter the original images to only to get the dog images. So that is a result. We only query the dog images. So the BigDL already provide many examples and the models. You can check our GitHub website, the wikis, to get more information. And currently, we already support the models like the LeNet, Inception, VG ResNet, RNN autoencoder, and we also have examples of the text classification, image classifications, and load models like the torch and coffee models. For the performance, BigDL have gained very good performance. We did the performance test on the Xeon E5 26 series V3 or V4 processors. And we tested on the single nodes, the BigDL can get the orders of magnitude speed up compared with the other out of open source frameworks like the Coffee, Torch, or Tiano. And because BigDL is original on the native Spark, and also by it's all reduced communications between nodes, so the BigDL program can be easily and efficiently to scale out to tens or hundreds of Xeon servers on Spark. And the BigDL also can work on the many different platforms. Here's a guideline to how to run the BigDL in the AWS EC2. And we already create the AMI for the BigDL, and we already have some example scripts to show how to run our examples in the EC2 environment. You can check the wiki page to try to run the examples, the Inception V1 or Perf examples in the EC2 environment. And the BigDL also worked on the other platforms. We work together with the Databricks and Microsoft Azure, and they design their programs, BigDL programs on their platforms and work very well. Okay, now let me talk about some real use case with BigDL. As everybody knows, the image recognitions and the object detections is very popular areas that's used in the deep learning areas. So there are many famous models, like for the object detection, the fast RCN and the SSD is popular models. And the BigDL, we already implement the fast RCN and SSD models. So we use these models. We can detect the objects in the pictures We can detect the birds and dogs and bicycles and stuff and these objects in the images with a very high performance accuracy. And for the natural language model, for the natural language processing, we already support the many natural language models like the RNN. Here's the standard RNN model, which is only have one single layer. And we use this model to learn the styles of the Shakespeare corpus. And here's the results. So after we training this model, when we input some trigger words, and the model can generate the rest of the sentences to mimic the similar styles of Shakespeare. And also we support the more complex RNN model like the LSTM. And now we already implement the LSTM such as GRU and LSTM with peepholes. And we have a real customer use case in the industry. The first use case is the transaction fraud detection. You know, the transaction fraud detection is very important for the financial companies. And a good fraud detection solution can save a lot of money for the company. So the company usually use the machine learning or the deep learning solutions to resolve it. And in this use case, we define our pipeline for our customer. All these components are on the Spark. And for the data, we store the historic data and the merchandise data on the Hive. And for the Spark, for the data clean and the pre-processing, we use the Spark SQL. And to do the future engineering, we use the Spark ML pipeline. And you can notice the green box. The green box is these part component that we use with the BigDL. So we use the BigDL to create the different models, and we use the sample and bagging strategy to handle the unbalanced data problem. And also we use the grid search, which is also on Spark, to tune the hyperparameters for all these models and to get the best performance. Another use case is about the product defect detection and classification. This use case is for our manufacturer customers. And the data is from the pictures that's the streaming pictures from the manufacturer pipelines. And our task is first, we need to identify the errors which may contain the defects. And then we do the classifications of the defects. And in this pipeline, also we create this solution on the Spark platform. And we have a very huge amount of high-resolution image as the data source. And we use the Keystone ML pipeline to extract the proposals, which is defect errors, and do the data processing with the Spark. And you can see we also use the BigDL to define the neural network, which is and to train the neural networks and test the data. And also we do some optimizations. And after we create this pipeline and we help our customer to improve the defect accuracy to 90% in the phase 1. So here's the link of our BigDL repository. So you can get the code or or wiki page, or everything is from that. And we also create our user group, the BigDL user group. And you can send any comments or open the discussions in that group. And also, we welcome the issues report and the feature report. Actually, we already complicate some features requests from the community. And we will continue to support it. Okay, let me continue my demo. Okay, I'll demo an example of the text classifications. The classification is to identify the class of some reports, text reports. And the data set is from the News 20 group, which contains 20,000 texts and with 20 labels. Oh, I'll enlarge it. Okay. Also, here's the Python code to do that. And this part is the library from the BigDL. And other libraries is some common used machine learning libraries and mathematical libraries. And first we define some utility functions, which is to do the data processing. And then we define some parameters for these examples. And here, we load the data from the local directory or download the data from the website. And then we create the RDD from the data. And then we do the analyze. This is the pre-processing of the data. And then we create the dictionary and broadcast to the cluster-wide. And now we prepare our samples based on the data RDD. We do some data conversions. We change the word to the vectors and change the whole text to the vectors. So that form our samples. So you can see this is how does the text like. So the bigger words is the words which have more frequency. Now we split the data to two parts. One part is the training data, and another part is the test validation data. And we define some ratios. In this case, we define the 80% data for the training and the rest 20% for the validations. And now we build the text classification models. You can see in this model, we define the reshape, convolutional layers, and the ReLU layer, and pooling layers, and etc., and linear layer. And after we create the BigDL, we create the text classifications with BigDL Python API, and now we create the optimizers. So when we create optimizer, we need to specify the model and also the data set, the training data set, and also the loss function when the maximum iterations or epochs, and also specify the batch size for each iteration, and specify the optimized method. We support different optimization methods like the SGD or adagram or LBFGS, and Also, for the optimizer, we need to set the validation, like the validation data set and batch size, and the trigger time, etc. And because we need to show the visualization on the TensorBoard, so we need to generate the log summary for our trainings. So we create the summary, the train summary for the training, and specify which kind of scalars we want to see in the TensorBoard, like the loss, the throughput of parameters, and then we create an optimizer with the adagram optimization method. Okay. After we create the optimizer, we call the optimize function, which will trigger the training. And because training takes some time, so I do this example before the demo, and to save more time, and you can see the result. Okay. And after we train the model, we can use the model to predict with the validation data set. So as you noticed, we use the adagram to train the model. So here's the result, the confusion matrix of the result. The x-axis is the predict value, and the y-axis is the true value. So you can see most of the data are in the diagonal. That means the prediction is correct, right? So, and we also did try to train the data with a different optimizer method. This time, we train the data with SGD algorithm with the same model. And here's the result. In the confusion matrix, you can see the accuracy is not very good, and there are only very few data in the diagonal. So that's because for the SGD training, we didn't tune the parameters for this training. So, and we only train for 2 epochs. So for the SGD algorithm, it is hard to converge with this condition. So, okay, so this is some histograms of the prediction values and the true values. And also, this is the diagram, the curve for the loss and for the accuracy curve. The SGD is worse than the adagram, and the throughput is similar on the mic system. Okay, now let's look at the visualization part on the TensorBoard. Oh, sorry. I need to run them all. Let me check whether I have a. Okay. Maybe I just clean the log, so we'll wait for the runtime training and the testing. Okay. I think Lennart is already done, so we can check the result of the Lennart example. So here's the result of the Lennart. Wait. Okay.
Internet? Okay. What about TensorBoard? Do we have TensorBoard for the net?
Okay. So the training for the text classifier will cost them about 2 minutes. So we can wait a little while.
Do you guys have any questions meanwhile?
Yeah, so does this support three-dimensional convolutions?
For the currently,
The question was, do we support three-dimensional convolution?
currently we didn't support it, but we are working on that. So we can later support the three-dimension convolution.
Guys, if you have any questions, we have 2 mics on either side here. Just feel free to come up and ask your question. That way we can capture the video as well as the entire audience can actually listen to what you're requiring. So feel free.
Thank you, Jules.
All right. Any questions?
Now, guys, I have the 10-page list of canned questions and answers. We're ready. They've been pre-approved by Intel Marketing.
Okay, so I heard that TensorFlow has been ported to Spark by another group at Yahoo.
Yes.
You know about that?
And the question is?
How does it compare with this offering?
It compares. Yes, I think it's a TensorFlow on Spark. If you look at GitHub, as I did this morning, you'll see that BigDL has much more committers and participants. The thing is, TensorFlow on Spark or Café on Spark, the way it works, this is the way I understand it works, is it allows you to instantiate multiple instances of TensorFlow or Café on your Spark cluster. What it doesn't allow you to do is to instantiate one and distribute the computation. So for example, suppose you have SGD, right? To distribute SGD and take advantage of Spark architecture, what do you want to do? You do what's called mini batch computation. You don't do that in Sailor, you kind of do that semi-drunk in Sailor. You break up your SGD into 10 batches. You run them in parallel on multiple servers, and then you, after each synchronous run, you compare the model parameters, you update the model parameters, and you take the next step. And eventually you converge. That's how BigDL works. That's not how TensorFlow and Spark works. That's not how Café works. You can instantiate 100 of them, but each one is going to run independently, and then you only have a very coarse-grained way of communicating between them.
Questions around the MKL. Is the MKL optimization only efficient when it's on the specific processors? Is it optional to BigDL? And if it's being run on GPU, does it have any performance gain, or is?
Okay, so let me start with the easy one. MKL does not apply to GPU.
Okay.
Intel versus NVIDIA.
Okay.
Is it exclusive to a BigDL? No. Intel has multiple other frameworks that take advantage of MKL, and they're also deep learning frameworks. They're geared towards a single node, highly optimized application. For example, if you want to run deep learning inside your car, you don't do it on Spark. That would be silly. Yet, if you put a Xeon processor inside the car, Intel has deep learning frameworks that take advantage of MKL, but they're single node and optimized.
So when I work with BigDL, is the MKL part, is it optional?
It is optional. You don't have to use it. It comes with it, you would probably have to delete it, but I don't know why you would want to do it.
No, it's not. BigDL actually reduces performance by using Intel map kernel library, so you have to, and it comes packaged with it.
Okay.
Yeah, so it'll be best to.
Yeah, it'll be best to use that. So
Thank you for correcting me.
Okay,
It's
so
very good to have a boss who actually knows technical stuff.
okay, so the training and testing is over, and we can see the result from the TensorFlow, which is a refreshed data. So you can see it's not fake. Yeah. So here's you can choose the log on this left side. Choose the log you want to show, and choose the scalars. The loss from two algorithms. One is the HGD and one is AdGram, and also the throughput for the two optimizations, and the accuracy. And also we have the histograms to show the parameters for the every layers. So you can check the BIOS, the weights and the grand weights and grand BIOS for each layer with this histogram. So use these visualizations. The user can monitor the training and the testing in the runtime and to improve or optimize their trainings. So yeah. Okay, are there other questions?
In the interest of time, we'll take only a couple of questions because we have another speaker following. So if you have any questions, please don't be bashful. The two mics are over here. Walk up. You bring a Fitbit, you might add 10 steps to it. Any questions? Going once, going twice? Okay.
Sorry.
We should get a t-shirt.
I'm totally hogging it. Sorry, guys. So it's probably a question for Databricks, but any time frame on availability on Databricks?
I think Gene actually had a URL up that actually showed the tutorial running on Databricks. If you actually go to the Databricks, when I go a couple on the stage, I'll show you the URL. So there's a tutorial available on Databricks, and there's a notebook that shows how DL is actually used. All right, thanks a lot. It was great to hear BigDL and structured streaming in one sentence. Oh yeah, no, one last question.
I saw in the slides you compare performance with open source, Cafe, and Torch. So you said like there are order of magnitude performance improvements. So what's the comparison like? How do you get this kind of performance enhancement?
I have a list of pre-approved questions and answers. That's not on it. I'll answer. Basically, we're orders of magnitude better than anything out of the box. If you took Cafe out of the box, plugged it on the Xeon server, BigDL would be better because it's very well optimized. You can do a lot of other optimizations. Intel takes benchmarking very seriously. We cannot tell you exact numbers. We've done it, and the results are right there. And that's it at this point.
All right, guys, give a big hand to Sergey and welcome back. It's really a pleasure to introduce my colleague from Databricks, Telegat Das. TD has been working with structured streaming, streaming of Apache Spark since the very early days when he was doing his PhD at MPLAB. And he's the guy who actually brought us D-streams. And those of you who actually be using D-streams, should be thankful to him. And ever since then, he has been working on this new idea about how you actually do writing continuous applications with structured streaming. And he's a committer of Apache Spark, and it's a pleasure really for me to introduce him and bring him and share us about what does it actually take to write structured streaming and why structured streaming is so important in today when we have data coming from everywhere and we have to deal with batch and real time together. So please give a big hand to TD.
Thank you very much, Jules, for that flattering introduction. So I'm here to talk about streaming. And, well, this slide Jules has already covered. So for people who have actually tried doing this, and also from others, they might actually know that building a really robust, stable stream processing application is actually pretty hard, because these applications need to do a lot of complex stuff. And if you think about it, you can divide this complexity into these three categories. One, your stream processing applications need to deal with all sorts of complex data from diverse formats, like you could have JSON, XML, Avro, binary, all kinds of different formats are out there. Data can be dirty, your data can be corrupted when you're getting data from IoT devices. Your data may be corrupted, or it may be out of order, it may be delayed because you're sending it over the wide internet. So lots of things can go wrong in the data. Then workloads, these stream processing workloads can be pretty complex. For example, one of the complicated ones is that people really want to do and want to do correctly, but it's hard to do, is actually doing event time processing, where you want to take the data and the timestamp in the data itself and do complex CEP style aggregations on the time, which is the event time itself. Then often you need to combine stream processing applications with other kinds of stuff like machine learning. You already saw the big data, the BigDL talk. People want to apply BigDL on streaming data. You often combine it with interactive queries. Your streaming data is coming in and you want to do interactive queries on the data in real time. So complex workloads that need to interact with each other, and you need to be able to reason across all of them that what are the guarantees that I'm getting when I'm processing this data through different workloads. And then systems are complex too. Of course, things will fail underneath. You have to be able to give end-to-end guarantees when things fail. What is the result that you're getting? Is your result anyway affected because of any failures in a distributed system? You need to deal with all different kinds of storage devices. For example, both stream storage devices like Kafka, Kinesis and stuff, as well as SQL databases, NoSQL databases, all files of different formats, Parquet, ORC. All of these you need to mix all of these into the same streaming application and reason about what are you getting out of it when you combine all of these together. So to simplify all of these, we built structured streaming. And what it does is essentially, it's a stream processing engine on the Spark SQL engine, so which makes it naturally fast, scalable, and fault tolerant out of the box. And we provide you rich, unified, high-level APIs, which allows you to deal with complex data, as well as complex workloads within the same engine and the same ecosystem. And finally, Spark already has a rich ecosystem of data sources around it, so it allows you to easily integrate with a very large number of storage systems, thus simplifying that another kind of complexity as well. And the key idea, the key philosophy on which we build structured streaming is that you, as a developer, should not have to reason about streaming. When you're building a streaming application, you should not have to reason about what happens when your data is late, what happens when your system fails, what happens if your data is corrupted. You should only have to write simple bash-like queries, and it is Spark's job to automatically streamify them. And that's the philosophy we started building structured streaming on. And so to do that, what we have done is essentially try to unify these two worlds, conceptually unify them, both static data and streaming data, into the single concept of tables. And essentially, you can treat a data stream, an infinite stream of events coming in, as a table which is continuously being appended. So it's like an unbounded table. So every item that is coming onto the stream is like a new row being added to the table, conceptually. Now, with this conceptual idea, we are proposing a new processing model for dealing with streaming data. And the model is as follows. So imagine your data stream is like an input table that is continuously growing. Now, when you kind of look at this table at every, let's say, every 1 second or every 10 seconds, we will call this the trigger interval. Your table, which is the input table, is continuously growing in size. Now, let's say you can define all your usual type of SQL queries, map, reduce, this sort of queries on this input table. And what you get out in the end is a result table. Now if you check this result table every 1 second or 10 seconds, this result table is continuously updating, continuously changing as more data is coming into the input table. Now what you finally care about is not the result table, is what gets out of the system. So ultimately you want to write the results, whatever has updated, to an external system, let's say a SQL database or a NoSQL database. That is what you really care about, what is output from the system to an external storage. And so you can define that every time I check this result table has some sort of updates, what gets written out to an external system. And that is called the output, and there are different modes of this output. Either, for example, let's say you are generating a table which is a bunch of aggregates. And so it's a very small table, and pretty much all your aggregates are changing all the time whenever there is new data. And you want to write this whole table every time to an external SQL database. So that we will call that complete mode, because you're writing the complete result table as output. Then there can be something like append mode, where, for example, you are just doing a plain simple ETL, no aggregations. You have essentially new rows coming into the system, and you want to filter some of them, you want to do some data transformations on them, clean it up, and then you want to write only the new filtered rows onto an external system. So essentially it's an append output. You're appending to an external system. And there are other outputs defined like update mode, etc. I will not go into those details, but what I just want to kind of propose here is that this is a new conceptual model which guides you how to think about your streaming application in terms of a query on a table. And even though I'm calling it table, and it is a conceptual table, because it does not mean that the engine underneath keeps around the whole table all the time. Once the engine streamifies it, it will keep around only the data that is needed for it. So that needs to be understood very clearly, that this is only a conceptual idea of a table. Now translating from this concept to actual APIs that which you will use to write your streaming applications, this unification of static and streaming data as a table allows us to use a single API, which is our dataset and data frames API, to run queries on both static data as well as streaming data, because static data is essentially a bounded table and streaming data is an unbounded table, and dataset and data frame is essentially synonymous to a table. You can, whatever operations you can do to a table, you can express it in the form of datasets and data frames. So using a single API, you can write both. Let's see a very short example of how this fundamentally changes of how you think about your application. So let's say you got a very simple job. You have a single JSON file, and what you want to do is parse the JSON file and select some of the columns, some of the fields inside the JSON file, and filter some of them and write it out to a Parquet file. So you would go in this manner, where you first define a data frame from JSON, you give it the source path. Then from that initial data frame, you create a result table. It's hardly visible. So you create a new data frame called result, which is the filtered and all the selection you have done, and then finally write it out as Parquet. Now to convert this batch query into a streaming query, all you have to do is this. Convert read on the top here to read stream. And what it means is that the path you're giving is a directory, and any files written into that directory will be considered as a stream of data. Your query stays exactly the same. The code of your business logic does not change. And finally, you want to write the stream out to a Parquet table, where a Parquet table will get continuously appended in the destination that you have provided. And so instead of what you did earlier, is that the final step was a save, which says that run this on the file and wait for the job to be finished. Instead, here you're calling start, which says that start this query and in the background, and keep running it continuously as new, and keep processing data in the background as new files get written to the source directory. So the key takeaway here is that all you need to change is the input and the output, but your core business logic stays exactly the same. Your code doesn't have to change at all. And for those people who have used these streams in the past, you can see that this is a step beyond these streams where you still needed to change the code fundamentally from compiling with RDDs to compiling with these streams. Here you don't have to, because all of this is just pure data frames. So underneath, what happens is that when you call start, what the system will do is that it will take all this code, it will generate a logical plan out of it, and this is the magic the Spark SQL analyzer optimizer does, is that it takes this logical plan, optimizes it, and instead of creating one execution plan that converts data once, the Spark SQL engine generates a continuous sequence of incremental execution plans from this single logical plan. And each execution plan is incremental because it knows that it has to take new data since the last time it had run on the data. It has to take the new data since the last time and process that and write it out. So it's Spark's job to figure out how to incrementalize or streamify your batch-like query into these series of micro-batch queries. You don't have to worry about actually dealing with the fault tolerance of that, because the system ultimately takes care of the fault tolerance as well. So all you have to do is enable checkpointing, and what it does underneath is that every time it has new data to process, it writes the metadata of the new data. Let's say, for example, you're reading from Kafka. Every time it finds new data in Kafka that it has to process, it will write the range of offsets from that new data that it has to process into a write-ahead log, so that in case of any failure, it can read back those offsets from the write-ahead log and re-execute exactly in the same way as it would have had executed if there was no failure. And because of the guarantees that the structured streaming sources and sinks provide, what the system in an end-to-end manner guarantees that you will get end-to-end exactly one's guarantees no matter what kind of failure there is in the system. So, and this avoids a lot of the problems that you need to reason about when you're building your streaming applications. So this was a very simple example I started with. Let's extend it to a more complex example, a more realistic streaming ETL pipeline example. So to give some background on ETL, traditionally the way ETL has been done is as follows. So you have raw, dirty, unstructured or semi-structured data coming in. What people usually have done till now is essentially dump the raw data without any sort of processing into files for doing the complicated processing later. And there are periodic jobs, let's say every 6 hours or every hour or every day, that takes the raw dumped files, processes them, cleans them up, does the transformation, converts it to, and finally converts it to more structured format so that you can run more complex queries like SQL and stuff on it. Now, the problem with this approach is that by the time you have to wait for hours for running complex analytics on the data that has been on the data in the stream, which is not okay if your application is time critical. For example, there's your intrusion detection applications, you have some intrusion detected. Now you want to dig deep and analyze what sort of intrusion it is, what is the source of the intrusion, etc. That needs complex analytics, maybe some machine learning algorithm you have to do on the data that is coming in right now. You cannot wait for hours for the data to be available for running machine learning on it. So time is of essence in such applications, and so this is often unacceptable. So the whole point of structured streaming is that we want to make this ETL process a pure streaming fashion where the structured data, the data coming from the stream is available to you in a structured form or within seconds, not hours of delay. So let's say here is a realistic example. You have JSON data coming from Kafka. Now this JSON data is very nested, so you have to parse the nested JSON data. You have to massage it. You may want to flatten it so that future queries become easier, and you want to write it out as more structured format, let's say like a Parquet table. You want to essentially get end-to-end failure guarantees because you don't want data to be duplicated in this process. So all the code that you need to write for achieving something like this is that's it. And I'm going to walk you through what each of these lines do, because it is important to understand that how simple it is and how to do such complex processing in these few lines. So step one, you need to read from Kafka. And so similar to reading from JSON files, all you need to do is specify the format Kafka. You need to specify which servers to read it from, so how to read it, what to read, which topics you want to subscribe, or a pattern of topics, or specific partitions in a topic. You have all of the flexibility in our Kafka source. You have to specify where to start reading from. So you will start reading from the latest available offsets, or from the earliest, or a specific offset. You can specify all of that as part of creating the Kafka data frame. Step two, now step two is you need to, now that you've created a data frame, you need to transform that. So the data frame that is created from this load essentially has these columns, the key and the value as binary data, the topic, partition, and the offset as all of these separate columns. Now you can use all of these columns here to now do further transformations. For example, I know that my data is JSON. So my first step is to actually convert the binary data into string as a JSON. So you cast the binary value column as a string, name it JSON. Step 3, I want to parse that JSON into individual separate columns. And for that, Spark SQL already has a very convenient function called fromJSON as a built-in library, which what it can do is take a single column of string, automatically parse all the data and convert it to a data frame having separate columns as a nested column structure. So this transformation allows you to create finally a data frame that has all the nested columns, all the columns you want to extract out of the JSON data as separate columns, and then you can do further transformations. For example, let's say I want to flatten these columns so that it's easier to store them. So that's again very easy, select data star, that flattens the nested columns. And finally, before the final step of writing out, I just wanted to highlight that so you essentially get a lot of the powerful APIs that you would want to do complex transformation as part of Spark SQL itself. And the advantage of having the single API and the single engine to process all of them is that all the complex APIs, all the complex functionality you had for data frames for batch queries till now automatically becomes applicable to streaming queries. So the final step is writing out to Parquet table. You just specify the final destination location, the format as Parquet, and you may also want to actually partition your data by time, because it's very likely that your downstream interactive queries that you want to do it on, let's say, last 1 day of data or last 12 hours of data. So partitioning the data by time is often beneficial for whatever post-processing you want to do. So that is also very easy. You just say partition by a particular time column, in this case date. And last but not the least, you need to enable checkpointing to get fault tolerance. And all you need to do is specify the checkpoint location, which should be a HDFS or S3 directory, or any HDFS compatible fault tolerant file system, so that if there is any failure, the system takes care of recovering appropriately from the checkpoint information in this location. That's all you need to do for writing an end-to-end streaming ETL query, or realistic one. And then when you call start, it actually starts that continuous query in the background in the Spark cluster, and it goes through the process of creating the logical plan and the series of incremental execution plans underneath. And what you get in return is this handle, this query object, which is a handle by which you can do any sort of management on the query. You can stop the query, you can restart the query, you can ask what is the progress, what is the ask for its metrics, performance metrics, its health, etc. So now, what this essentially did is that you're reading directly from Kafka and directly writing it out as Parquet table all within seconds. And so as this process is going on in one Spark cluster from a different Spark cluster, you can immediately start using that Parquet table for interactive queries, and you are guaranteed to get queries running on data written in the last few seconds. And I wouldn't go into a lot of detail, but what the structure streaming guarantees is something called prefix integrity, where it guarantees that whenever there is a batch of updates written to a Parquet table, either you get to see all the updates or none of it at all. So it gets some sort of a transactional guarantee that you don't see inconsistent data. Either you see all the updates that has been written to the Parquet table or none of it. And I won't go into more detail about this, but do refer to our blog for understanding what prefix integrity means and how it differentiates Spark structured streaming from every other streaming engine out there. So this was still among the simple, most common, but among the simple use cases. What often people want are more complex use cases where you want to do aggregations and stuff. Let's walk through some of them. So as I mentioned earlier in the beginning of my talk, event time aggregation is one of the more complicated stuff that people want to do. And for example, you have data coming from your IoT devices, and you want to understand what are the number of errors that your IoT devices have faced in the last 1 hour or in the last 10 minutes. Is the rate of error increasing, etc. Now, this is one aspect where dstreams, for those who have actually tried using dstreams, the API itself was fundamentally insufficient for building event time based operations, because it was not designed for that. And this is what we have learned in the last 4 years while working with actual applications and hundreds of actual developers. And that led us to think beyond dstreams and think about structured streaming from scratch. So, and as part of this, we had to actually solve a bunch of challenges, like how do we handle late data, how do we handle out of order data, how do you reason about when things are out of order and stuff. So, but again, the philosophy is that you should not have to worry about that. So all you need to worry about is how to write your streaming application, and that we have made that very easy. So let's say you want to do window-based aggregations. Let's say you want to get the number of events you have seen in the last 1 hour window. So all you need to do is basically write this query. And so here the window essentially becomes a very special case of group by. You're grouping by a window based on a particular time step column and a particular window length. And that's all. That's all you need to do event time windows, for which this would have been much more complicated in dstreams, but here it is very easy. You can also group by not just the window, but also group by both a device as well as a window. So if you want, for each device, what is the average number of, what is the average signal strength every 10 minutes, then this would be the query. Again, very simple, very SQL-ish. And for those advanced users of Spark SQL, this automatically supports user-defined aggregate functions that we have always had support for in batch. This automatically works on streaming queries as well. And to do these aggregations, a fundamentally hard thing that we needed to do is actually do stateful stream processing, because between each incremental execution on new data, you need to maintain the intermediate aggregates, the running aggregates or the intermediate windowed aggregates as fault-tolerant distributed state between these executions. And this state needs to be fault-tolerant because in case anything fails, you need to be able to, the system should not forget the intermediate aggregates. It should recover them. So that's why it needs to be fault-tolerant. And so this state is maintained as an in-memory state in the Spark workers, backed by write-ahead logs in HDFS or any HDFS compatible file system. So the system automatically figures out how to write to the state, make it fault tolerant, and every incremental execution reads the previous version of the aggregate, the state, and write a new version of it. All that is taken care of by the system underneath. You don't have to worry anything about it. And the system guarantees end-to-end exactly once guarantee, despite any failure. But now, for those who have actually dealt with this kind of processing systems, a very complex problem is that how do you decide when to actually forget the state. For example, I want 1 hour window counts, but I really don't care about the count that is 1 week ago, because I've already dealt with it. I want the system to forget about it. And but if the system doesn't forget about it, then these counts will keep accumulating the memory and blow out of the memory. You don't want that. So for that, in Spark 2.1, we added this concept of watermark. This watermark is essentially a moving threshold that is trailing behind in terms of event time, trailing behind the latest data, and which defines the threshold that the engine will not care about any data or any aggregate that is older than this moving threshold. For example, let's say the max event time that you have seen in your data at this point of time is, let's say, 12:30 p.m. And you've defined your this trailing gap for the watermark as 10 minutes. So then the watermark is currently at 12:20 p.m. And what the system will do is that it will not remember and clear of state that anything that is older than 12:20 because it assumes that you don't need anything older than 12:20 p.m. So this means that any data that comes out of order but still within at most 10 minutes delay, those data will still be considered for aggregations, for operations and stuff. So, but data that is older than 10 minutes, basically it came more than 10 minutes late, will be dropped by the system, because the system kind of filters them out, because it aggressively tries to minimize the state it needs to keep. And so it forgets anything that is older than 10 minutes. In this way, you can do a trade-off between how much state you want to keep versus how much late data you want to allow. If you want to allow more late data, not just 10 minutes, let's say 2 hours of late data, your data can be that late, then your system will have to keep state related to last 2 hours of data, and will therefore be more state. But if you don't want that much, you can trade it off to keep less state into the system, therefore need less memory in your cluster. And to configure watermarks, all you need to do is this additional line where you say how to define the watermark, which column to define the watermark on, and what is that configurable delay between, or how late is the data allowed to be. That's all. And the system takes care of all the tracking underneath it. So whenever there is data coming in, and this is a kind of complicated figure, I will not go into a lot of detail in this, and this figure is explained in more detail in the structured streaming programming guide. So I highly recommend you to actually go ahead and read that. But at a high level, what the engine automatically does is that it will scan the data every time there is data and figure out what is the max event time at any point of time. And based on the threshold, it will figure out what is the watermark threshold, and accordingly consider when new data comes in, is it newer than the threshold, in which it may be late, and it will still consider it. But if it's older than that watermark threshold, it will automatically drop it and not consider it anymore. Anyways, so this is, more details are in the programming guide, so please check it out. And then a more advanced thing for those people who want even more advanced stateful processing stuff, where you want to customize the state you want to maintain for time, to do some sort of sessionization and stuff. In 2.2, we are adding map groups with state, where you can do arbitrary stateful stuff. For example, the way to do it is that you can maintain user-defined state for every key or every group. For example, let's say you are monitoring live videos, and you want to, for every video, you want to maintain the current status of how many errors the video has seen, how many, what is the buffering rate and stuff like that, so that you can see how many videos are in a bad shape. Then all you need to define is that for each video, given the previous status of the video, the new events that the video has sent to your system, what should be the updated state. You define that function as in this sort of mapping function, and then you apply that mapping function on each group, where you group by the ID of the video, and then apply that mapping function as map groups with state mapping function on that video. And the system will take care of automatically partitioning the data by the video ID, and apply the function whenever there is new data for each of the video. Also, it supports timeouts that, for example, for a video, if you haven't received any data because the video lost connectivity abruptly, you can define timeouts that you want to basically clear off the state that this video is defunct right now, so I don't need to maintain state for that anymore. So there is support for timeouts, by which you can clear off state and stuff. These timeouts are very customizable. Right now, I'm actually right now in the process of updating the programming guide for giving detailed instructions for this. So stay tuned for the Spark 2.2 release, hopefully within the next month. And you will get to see a lot more detail about this. And for those who have used dstreams in the past, this is essentially, in principle, exactly like update state by key and map with state. But this applies on data frames. Anyways, I cannot talk about all the stuff that we have added. We have been moving. This is one of the fastest moving sub-project inside Spark right now, and we have aggressively added a lot of stuff. I cannot talk about all of them, but some of the highlights are we have added streaming query listener in 2.1, which essentially allows you to give asynchronous updates on the health and performance of your streams. You have added streaming deduplication. This was actually a highly requested feature that over the last 3-4 months, people have asked us to do that, and we actually implemented that by public demand, where you may have data duplicates because, for example, Kafka doesn't give you exactly once guarantees when you write to Kafka, so you may get duplicates if you're using Kafka as your source. You can use this deduplication operation to automatically dedupe your data from Kafka and get stronger guarantees in an end-to-end manner. We have obviously added a lot more Kafka integration. We have not just the Kafka source, but we have added Kafka as a sink, so you can write it out to Kafka directly as easily as writing out to Parquet, though you don't get the exactly once guarantee because Kafka doesn't support transactions yet. You can also run batch queries on Kafka. Similar, so Kafka, and you can treat Kafka pretty much like a file system as well. And we're also in the process of adding Kinesis as a source as well. Future direction is, I think, the most important thing is stability for the whole system, for all the operators. So it is currently marked as experimental for the open source, but internally we have been running it in production for quite a while. Our customers, few of them are actually also running it in productions. I recently spoke at Strata San Jose a couple of weeks ago. There I found some people in the open source are also running it in production, so people are using it, but it's still marked as experimental because we have to first add all these basic operators and test it for stability and fault tolerance and add more sources before we can actually truly mark it as production ready so that anyone can use it without having to sweat about it. So that is our highest, most important task right now, and hopefully within by 2.3 we can actually mark it as production ready. As part of that, obviously we want to add more operations, and one of the highly demanded feature is stream joins, which we don't support yet, but we support stream batch joins, but not stream joins yet. We want to also stabilize the source and sink API so that you can write your own sources and sinks for your own storage systems and stream sources. And we definitely want to add a few more inbuilt, like JDBC as a sink, so that you can write out to any SQL engine that supports JDBC and stuff. So lots of stuff that has been going on, lots of stuff we need to do. This is very active. Please use it, provide feedback over the mailing list. We really try to answer all the questions that we get with mailing lists because we really want you to actually use structured streaming. This is the future beyond these streams. And we write a lot of blog posts highlighting each of these operations and stuff, how to use them. They're more tutorial style blog posts. So please stay tuned to the Databricks blog post, and we are hoping to write almost 1 or 2 every month, so stay tuned. And a sneak peek from the blog post is that a lot of you who haven't heard about structured streaming before might be wondering how does it compare to other streaming engines out there. There are many, and one of our blog posts actually covers this, and it has this table on each of the individual features that we support that others don't. So please take a look at our blog if you understand how does it compare with other engines. Anyways, if you want to learn more about what's not just structure streaming, but all the latest and greatest stuff happening in Spark ecosystem, please join us at Spark Summit. It is within a couple of months. The registration is open. The early registration deadline is soon. I think Jules can. April 7th is the early registration deadline. That's a big price difference between early and not early. So highly encourage you to actually register for Spark Summit. And before I finish, actually Jules here actually has a very cool demo about how well structured streaming is actually integrated onto our Databricks platform. And hopefully it gives you an idea of how structured streaming can simplify building your stream processing applications.
Assuming that the demo goes are in my favor. Can you guys actually see the screen? Okay, how about now? You can? You're going to go blind, are you? Okay. How many of you are actually using Databricks platform? Anybody here who's a Databricks user? Brilliant. If you want a t-shirt, raise your hands. I can bribe you. Brilliant. Okay. I'm not going to show the entire demo, but this is actually what the Databricks platform looks like when you actually log in. This is your particular screen, and all you're going to see is a very simple screen, but all the complexity is actually hidden behind it. And I really wanted to point out to this particular pan over here, where if you're a user, you actually get up-to-date over everything that's actually happening. We release new bits every 2 weeks, and if there are any patches that we have actually included in the open source, you actually get it as one of the first things. So very easy to create a particular cluster, but I won't go into the details about how to create a cluster. That's for another time. But what I have today is the structured streaming demo. Now think about, I could have millions of devices which are posting these particular events on periodic basis using Kafka. But for the sake of demonstration, I'm going to have a Kafka server here. Think about these devices that have already been created and are stored in an AWS bucket. So over here, I have my bucket that has all these particular JSON files. And each JSON file actually has a bunch of events that looks like.
Second level, it's pretty much the same as these trees.
So each JSON file actually looks like this. So you got an event that actually has a device ID, device type, sensor, collects the temperature, gives it the signal, how the battery is doing, what the CO2 levels are. So we want to monitor about how environmental friendly you are. And these are actually live IP addresses. These are not fake IP addresses. And so there might be some offenders over here who actually have devices in the factory that's emitting 13 or 1400 levels of CO2. So what I'm going to do first is show you how you actually do that in batch. And I'm going to do exactly the same thing, showing you how you actually do in streaming. That's what Kenny talked about, which was you just have to change one or two things in order to do the streaming. You can actually see real-time data. So what I'm doing over here is, in order for me for Spark not to infer the schema, I'm going to provide the schema, what the schema looks like, what my JSON file looks like. I have a bunch of struct, single type, long string, and so on and so forth. So let's do that. And I'm going to set the shuffle partition to be ones because I have a small set of data, but this is again just for the demo purposes. And I'm going to read my entire JSON file, my entire batch in one go. And I'm going to cache the data. And I'm going to show you what the device looks like. So here's our data frame that actually has all these column tables, and we sort of programmatically, we've grown up to look at things in a very structured manner. So this is what your data frame actually looks like. And you got 2,400 devices in there showed here. Now I'm going to do some batch processing. I want to find out, for example, in this particular piece of code, how many devices whose signal is less than 15. And if the device has a low signal, then the chances are the battery is dead. The battery could either be 0, it could be 1. So I'm just going to do a batch, just in one count, and do an aggregation of it for batch mode. So we'll go ahead and do this. And what you actually see over here in my display is the batch mode, right? So here's the data that actually shows me in batch. I read the entire thing in one go, and that's what it looks like. So we got an iPad that is about 290 devices whose battery is 0, is completely dead, and then we have an equivalent of that which has a battery 1. So this is not good for a factory that has all the devices in there. And note that I issued this particular query using the data frame API, but I can use an equivalent way of expressing the query if I actually did using SQL. So over here, I'm doing exactly the same query using SQL for a table that I actually created over here. You see this guy over here? That's a table that I actually created for my data frame, and I'm querying that table temporarily, and I should actually see the same data, identical, exactly the same query, using the data frame API or using SQL. And the good thing about the notebook is that you can actually, within the one cell, you can specify Python code, an SQL code, or your regular Scala notebook, and this is a Scala notebook. Now, what about if I actually wanted to do the same thing in streaming, which is that was the gist of the talk today, is that anything I can do in batch, I can do in real time with streaming. So what I'm doing over here is pretty much the same thing. I'm reading now the stream of JSON files, which are now in the directory, but assuming that I could actually read that from Kafka. But what I've done is I've taken all that from Kafka and I've dumped it in the directory, about 24, 25 files. And what I'm telling the source or the streaming engine is to take one file at a time, depending on M time of it, as my trigger, and then do the processing and read that particular file. And each file has about 100 devices or so. Let's go ahead and do that. And then I'm doing exactly the same query, right? All I did was, before my batch, I'm saying select that particular device type, the signal is less than 0, group by the battery, and then do that with screaming and do the count. And then you see that this particular frame is actually a streaming frame. As a query is df, a streaming frame that returns me true. Now I'm going to go ahead and display this particular frame in real time to see what it looks like. Okay. So it's actually computing things in real time, and you should actually see the table being displayed as the data is coming. It's processing in real time, and it's updating as one file is read, and it's doing the aggregation in real time. So by the time this data actually comes in, I should actually have the equivalent chart as one that actually showed in my streaming. Now, if I actually want to find out how my streaming job is doing, what I can do is I can go to this particular display query and actually find out how my streaming is monitoring, whether I'm lagging behind, what my batch, how my triggers are executing. And over here you can actually see I'm getting 20 records per second, and that's sort of telling me the health of my devices, or my streaming engine as it goes on. And you can see as each and every batch or each and every trigger is being executed, this particular chart is being actually updated in real time. So at some point, this particular chart is going to look identical to the one that I did for the entire batch. And that's the whole idea, that's the power that I really didn't have to do too much in terms of changing things. All I had to do was specify that I'm reading it from a stream, I'm using a trigger one file at a time, and give me the aggregate of all the devices whose certain conditions meet my criteria, and I can do that in real time. So hopefully by the end, in a few minutes, we should actually see all the files being processed. You can do something else. TD talked about one of the great things about Window is that you can actually find out window aggregations by event time. So if you have devices coming in at a particular time and you want to group them by a certain amount of time in the timestamp of the actual device, not the time when it arrived, but what was the timestamps of the event, you can do by window operations. And over here, in this particular code, I'm doing the same thing, except that I'm saying, go ahead and group by the timestamp of 5 minutes, right? Read each and every trigger, but group them by 5-minute intervals for the event time. So let's see what it looks like. Very simple. I'm going to go ahead and execute that. And it is a streaming, and I'm going to go ahead and display that. Is this finished? Over here it actually tells me now this job is particularly finished. And if I look at this particular device, exactly the same thing as the one that we actually did earlier with SQL, 290 devices. And this stream job has been finished. As you can see, the number of records are 0. So So that job is actually finished. It's processed all the 2,400 devices and about 100 files. And this is now my device. This is the new stream that I'm just doing windowing by aggregation, which what Tini talked about was group by window is just another group by function, and this is actually happening in real time. So if I actually look at my health of that particular stream, that's actually telling me again how the stream is progressing as the data is coming in, and I'm updating those in 5-minute intervals. And you can actually see in the first 5 minutes I had about 26 devices of type. You should have of type sensor, iGate. These are all the different devices. And I can go further ahead, as Tini pointed out, that you can actually do continuous aggregations. Suppose if I wanted to compute averages as I'm going along and streaming data is coming along. So here's another very simple device that all it's doing is group by the device type, time step window, but I want to take an average of the signal that's coming in, because these are important IoT devices that you're actually monitoring in real time. When you want to do something, as soon as something happens, you can notify the node, you can notify the people who are taking care of your operations data center. So we do a group by, and I do display query over here. We should actually see the average signal. Let's see how we're doing over here. So we should finish this pretty soon as more data is coming in. All this actually happening in 5-minute window intervals. And again, these are all the average signals. Again, as data is coming in, I'm updating this particular figure at a time. And let's see what is the data showing over here. About 20 records per second. And then I can do the third thing. I can go ahead and say, okay, what if I actually want to find out what are the countries which are the offending countries that actually have the CO2 levels that go above 1,300. We want to find out who they are and have Donald Trump have a chat with them, but I doubt that will happen. But let's try that anyway. Okay, so let's do a continuous aggregation on how we're doing. Okay, this signal is still going in time. We'll actually do the offending countries. Let's find out who they are. I'm going to go and do a display of this screen. This is going on. Brilliant. So here are all the countries. Some of them, let's see, where is USA? Oh, 17 devices. I wonder where is that? Another one is Italy. That's got 10. China, 11. We'll find out how many are at the end. So let's see where we are with this particular stream over here. It's almost done. And these are all the different average signals of each and every device type. And the highest signal over here is about 18.4. So what I demonstrated will be a number of things. You can actually do the whole batch in one go, or you can actually do real-time streaming in incrementals of triggers, or you can actually do it as you're reading from Kafka. You can do aggregation as you go along, and you can actually do a windowing of the event time, all in very simple APIs. And that's the beauty, that's the power of what Tini was talking about, that the continuous application allows you to do that end-to-end application. And you, as a developer, need not worry about all the underlying complexity of state management, of fault tolerance, of idempotency, all that's actually taken care of. And then finally, I think we're almost done here. Let's see. Yeah. So that essentially was a quick demonstration of some of the high-level APIs. I mean, we are going to be showing this end-to-end in a full, more high scale with large clusters and Kafka running. But here, just for the sake of demonstration, we just had to sort of show you what are some of the salient features of the API. And finally, somebody actually asked me, it was you, you know, how does BigDL work on Databricks? This is actually a blog that actually has a tutorial that demonstrates the intel. So at this point, I think the demo is over. I'm going to have Tini come back and take any of your questions that you have that you are probably dying to hear. There are 2 mics on either side. Please do come. I don't want to run up and down.
what can we expect if we want to move to this? This is still experimental, as you say. In terms of performance, I'm thinking, what can we expect if we kind of rewrite the application?
That's a very good question. So the question was, for those who didn't quite hear it, that he already has a DStream application that they have hand-tuned the performance. How does the structured streaming performance compare with DStreams? So that's fundamentally, these streams were built on RDDs, whereas structured streaming is built on the data frames of SQL Engine. So in SQL Engine, we have added, over the last 3 years, a lot of stuff that makes it 10 to 100x faster than the pure RDDs, and much more stable in terms of memory consumption, etc. So since structured streaming is running directly on top of that SQL Engine, the performance will going to be night and day.
Okay. However, we don't get as much control as we get with DStreams, is what I'm learning. So, the hand tuning that goes into DStreams gives you a lot more control, and we lose some of that here.
So I'm not sure what sort of optimizations you're referring to in terms of hand tuning. For example, if you're referring to the number of partitions and stuff like that, that you do get out here through SQL configurations and stuff. If you are trying to hand tune things like partitioners and stuff, yes, those are still work in progress inside the data frame side. So yes, a lot of the things you can hand tune here as well. There are gaps, but what we think is that given the huge performance bump between RDDs and data frames, you probably don't need to do a lot of those hand tuning and stuff.
Can I ask you a very specific question about that?
Specific questions in your application, let's take it offline.
Okay, sure.
Yeah, let's do it later. Yeah, go ahead.
Hi. You showed some code about window that was based on one of the attributes of the event, which was event time, 1 hour or whatever. I think you mentioned something is coming in Spark 2.2 that will allow you to define these operators based on other attributes. Did I get that right? So for example, if I want to define a window that's not based on time, based on number of events or some other attribute, is there a
okay, the native window support is based on event time and time windows and event time. But in 2.2, we are also adding map group with state, which is like a generalized stateful operations. So there you can implement a lot of the more custom windowing stuff by maintaining your own list of events, list of last n events as a state. So you can implement your own windowing if you need to, using that operation.
I think if you implement your own user-defined aggregators, that along with the use map state, you can actually say, if I reach that many processing, if I map that many events, then go ahead and do something with your map state. I think that's what he was referring to.
One of the questions related to the state management. So, in terms of storing that state, do you have APIs to kind of store any kind of state and retrieve it? Besides the standard aggregation APIs that are exposed?
Yes, you can. So with the power of datasets and dataset encoders, we can convert any custom classes for defined in a particular way. For example, in Scala, you have to define case classes. In Java, you have to define Java beans. But once you define the classes in that way, we can convert and encode any of custom classes into our own internal encoded format and do processing on them.
Oh, thank you.
Go ahead.
Yeah, thanks. Kind of a direct follow-up on that. Has there been any benchmarking on how large these state objects can get before it starts causing trouble with the larger system?
It totally boils down to how much memory you have in your workers, and there is a lot of work that needs to be done to make it more robust and stuff. But at this point of time, it is as robust as these streams have always been. That is not the upper bound, so we still want to do more work to make it even more robust and even less corner cases and stuff. But as of now, it's already as robust as these streams ever was.
Any other questions? One more.
to follow up on the answer on that, so for a lot of use cases, like especially Windows, the memory consumption is by far much lower compared for structured streaming compared to D streams. Because, for example, the way windowing was done in D streams, if you want to do window over 1 hour, you'll have to keep the raw data of 1 hour in memory, which is a lot of memory usage. Here we don't. Here we do windowing in a fundamentally different way, which doesn't require you to keep 1 hour worth of data in memory at all. I mean, you just don't have to keep any data, only the intermediate state in memory. So in that way, the memory consumption for a lot of operations is much, much, much lower in structured streaming compared to the equivalent operation in D streams.
Okay, we only got time for only 2 more questions. Go ahead.
Fantastic. Just a quick question on, you mentioned Parquet and also the possibility of that you have data coming in when you put in Parquet format, and it's either all the data is present or nothing is present. And also there was another disjoint thing about idempotency. I mean, maybe are these related, or like how does the system handle idempotency, and is there any sort of consistency guarantees also which it provides?
That's a very good question. How does, when you're writing out to Parquet, how does the system maintain consistency guarantees, or especially the prefix integrity that I talked about very briefly? So while writing out to Parquet, what we do is we maintain our own metadata of what files have been written out to Parquet, what are the appended new files to it, and so this metadata is present in the directory itself where it's been written out to. So when you're querying the same directory through Spark using some sort of batch queries or interactive queries, it is aware of that metadata, and it can, through that metadata, additional manifests. It can guarantee those. It can give those guarantees that either it sees all the appended files or none of it, and it can give that consistency guarantees.
But still, it would be some sort of like log structured merge trees underneath, or
no. So to go into a little bit more technical details, in Parquet you can write additional files. You're not appending the file. You're just writing new files, right? So all you need to do, all we essentially do is in our Spark custom manifests, we specify what are the new files that have been written. And while running a new batch query on top of it, if it finds the manifest, it can understand them and automatically understand, okay, either read these latest whole set of new files that have been written, or read none of it at all. So the manifest is updated in an atomic manner.
Yeah,
we have to. We'll take someone up. We have to take last.
We'll just put this offline.
Yeah.
I think you want to move a bit more technical details, which let's talk offline on that.
Yeah. We're going to be around.
About state and snapshot files. So you said like HDFS and S3 are supported. So what happens if it runs not on Hadoop and not on AWS? Meaning like you want to persist in Cassandra, Couchbase, here. And from your experience, what is the typical size of those files? The question, like, because HDFS doesn't like small files, and NoSQL databases don't like huge files.
Very good question. So right now the state is kept in memory and persisted as write-ahead log files in HDFS compatible file systems, including S3. But it automatically does compactions, etc. in the background. So it's not the most efficient. It's kind of a generic dumb implementation. What we plan to do in future is to clearly define and open up the state store APIs so that anyone can implement their own custom state store. Maybe that may be like Cassandra or some other database while using the state store APIs. And so then it would hopefully be very easy to run structured streaming queries unmodified against state stored in Cassandra, for example. So we do want to open those APIs up in future so that it makes it much easier for users to scale on using custom databases and stuff. Regarding how much is the memory usage and stuff, it is so heavily application dependent that it's hard to give a good answer to that. what I can say is that it scales naturally to the size of the Spark cluster. If you want memory, just add more workers in your application, you get more memory. So, but definitely we can improve. We can do more improvements on the memory usage and stuff. That is definitely what we hope to do in the near future.
And do you have any statistics about like a snapshot file sizes on the disk?
Again, it totally depends on what, so how much data you're writing. So if your data, so what I can say is that if your in memory representation is takes 1 GB, then the snapshot files on the file disk will also be roughly 1 GB-ish. No, well, 1 GB compressed from a 1 GB, which depending on your kind of data it is, you will get good or bad compression.
Okay, well, thanks a lot for coming. Give a big hand to TD.
Thank you very much.
And I wanted to again thank Julia from Intel for coordinating all this and making things a bit easier for us. And again, don't forget to attend Spark Summit in June. We have early bird registration going on. You can probably save a couple of $100. If you do want to speak at Spark Summit, if you do want to host us, if you do want to sponsor us, please come and talk to me. And we do want to have as many speakers in the peninsula, so that way you don't have to drive all the way to San Francisco. But again, thanks for coming, and I hope to see you in a month. Cheers. Bye.